Alright guys, so this is the second video for this specific question, and I've already gone through part A and B, so if you've not seen that, you can go check them out very quickly on my page. They should be the previous video, but in this video we're going to go through part C and D. So part A and B kind of concerned parametric differentiation, whereas now these parts, they concern parametric integration. So this video is going to be quite long, because the question is long, I'll be real. It's kind of requires a lot of computation, like a lot of writing as well. So it's going to be a while, but just stick with it, stick through. And you can even try it, have a go at it, see if you get it right. And yeah, so pause the video, have a go if you would like to, and I will go through the work solution. Okay, so let's just read the question. The finite region S, shown shaded in figure 6, is bounded by the curve C, the line L, the y-axis, and the x-axis. And it wants us to show that the area of S is given by this horrible thing. So don't be like worried or alarmed when you see that. Obviously, that does look really AIDS, but it's not that bad. So don't worry. Just try and stick with it, kind of split the question down and see what you can do, because it is 6 marks, so there is a lot of opportunities to pick up some easy marks as well. Okay, so before we even dive into the question, we want to try and figure out how to find this area of S. So what this requires is you actually need to split this kind of region into 2 parts, because here we have a Cartesian equation, which is line L, and we also have a parametric equation, which is curve C, and we can't kind of deal with those as one thing, because Cartesian and parametric, they don't just go together. So in year 1, you might have understood that if you had 2 Cartesian equations, you could do the top line or the top curve minus the bottom line or the bottom curve. But with this, it doesn't work like that. So we need to treat these 2 things and try and find integrals that work separately. And then once we split the regions and found the areas that are kind of corresponding to each of the regions that we found, we can then add them together. And you'll see what I mean. So with this, what I would do is I would split this region down like this. And this is because we can label the 2 regions. So we split S and we can label each region R1 and R2. Now with R1, we don't actually need to do anything with the parametric equation. We can kind of just integrate line L between this limit and this limit here. So that's very easy, we can do that. Now in terms of the R2, which is the parametric equation, we don't need to involve line L. We can just use parametric integration to integrate that. So we just need to find the limits of here, and again, use that same limit there as well. And then we could just add these together and find the area. So that's what we're going to do. Now, before we do that as well, I just want to also go through how to do parametric equation integration very quickly. So all it is this formula here. So you integrate, you find your limits, y, you times it by dx over d theta, and then you times that by d theta. And this is because if you use your common sense, these 2 things will just cancel out like so, and then you end up with the integral of y with respect to dx, which is what we want, which is what we usually work with. So we're going to find the limits first for R2 now. So we're going to work with R2 in terms of the limits, and then we're going to kind of switch to R1. So this is how I do it. There is multiple methods. Sometimes you can just stick to R1, find it, and then go to R2. I just did it like this. It doesn't really matter, to be honest. So in terms of the limits, we want to find this point here. And this point is where y is equal to 0. So we need to find where y is equal to 0. So we just set 6 sine squared theta equal to 0. And you should know straight away that whenever you have a sine function like this equal to 0, theta will just be 0. So we can set our limit to 0. This is wrong, and I'll explain why that's wrong. This should be upper limit. This should be the lower limit. So now we need to find this point in terms of theta, right? This black point here. And we already have that. That's because it's point P. Theta is pi over 3 at this point. And the reason why I switched the limits, so 0 being the upper limit and pi over 3 being the lower limit, which might seem quite strange because 0 is smaller than pi over 3. But if you look at the graph, this point here is where theta is pi over 3 and this is 0. And usually what we do with integration, the kind of upper limit is the point before the point on the right-handmost side. So this would be the lower limit, and this would be the upper limit, right? Because we're kind of integrating this way. So we go the lower limit and then the upper limit. So don't kind of be alarmed if you get that, where the upper limit is less than the lower limit. That's fine in parametric integration, and even any other types of integration as well, because usually a question is designed like that to trip you up, but there is a trick around that, which I'll get to. Okay, so we've got that now. So we've got our upper limit and lower limit. Now let's move on to R1. So R1 is really easy. All we need to do is we need to integrate this equation, which is x plus 3.5, with our limit. So of course, x here is just going to be 0 because it's at the origin. And then x here, we already worked out the x value in terms of Cartesian is 1, right? So we just need to integrate between 0 and 1. So once we integrate that, remember year 1 integration, I'm not going to go through it because it's so easy. If you don't get it, then and you're in year 13, then that is a very bad sign. You need to really go and revise. So that's why I'm not going to go through it. But you end up, once you plug in all your values, you end up with 4. And that's kind of like a good sign because we have a 4 here. So that's a good sign already. So that's R1 done. And notice how, in terms of the form that I want it in, if we didn't need to integrate it, there would be 2 integrals, right? One separate for R1 and one separate for R2, which is probably this whole thing here. But notice that there's only one integral, which means that we had to integrate R1. Yeah, to find R1. Okay, so R2, this is where it gets a bit tricky. So in terms of R2, we have our upper and lower limit, which is 0 and pi over 3, like I said. So if we use our equation, so we do y times by dx over d theta times by d theta. We've already worked out dx over d theta in the previous part of the question, which was minus 24 cos squared theta sine theta. But there is something you need to notice here, and that is the fact that if you times these together and make it one function, there is no way in which it could equal this, where there is a minus separating 2 different functions or 2 different kind of entities within the integral. So we need to do something about that. And the most obvious thing is to convert either sine into cos or cos into sine using the trig identities. So you should notice that if you convert sine into 1 minus cos squared, when you times it out, so like this, you end up with this. And this looks very, very similar to what we want. Now, another thing we can do, sorry, I'm forgetting the d theta there, that's my bad. But another thing we can do is we can take out 144 as a factor, so we end up with this. Now, this is where the upper and lower limit things comes in. Now, notice that we have it in this form here, right? This. But we want this, in the form that I gave in the question, we want this to be a minus, and we want this to be positive, right? And the way we can do that is to kind of flip the sign within the integral. We can flip the limits, so we can turn the upper limit into the lower limit and vice versa. And then once we've done that, we can then flip the sign inside the integral. So I flipped the upper and lower limit so that pi over 3 is now my upper limit and 0 is my lower limit. And then I've also switched the signs within the integral. And that is exactly what we needed here. So now we're missing the plus 4 obviously, but we found that, which is R1. So we just find the total area, which is R1 plus R2, and we end up with this, which is exactly what we need. Nice. So that was long, I can't lie, but if you got that, good work. So part D now, all it is just finding the exact area of S. And this is quite easy. This, you should know if you've done enough practice, it's just reverse chain rule. So I'll go through reverse chain rule very, very quickly with you, just in case you don't understand it. So reverse chain rule, where is it? So much writing, I've forgotten where it is. Here you go. So with reverse chain rule, what we need to do is we need to realize that there are 2 functions, 2 separate functions, and the derivative of one of those functions is also within the whole function itself. So that might sound really confusing, but you'll see what I mean. So I'm going to make a guess here, right, in terms of the integral. So I think that the integral of this is going to be cos theta all cubed, right? And what you want to do with that guess is you want to differentiate it, yeah? So how I've written it is dg over d theta. You don't have to write like that, that's how I prefer it. And when I differentiate it using the chain rule, I end up with minus 3 sine theta cos squared theta. Now you should notice that this is very, very similar to what we need, which is this. The only difference is that this is minus 3 sine theta cos squared theta rather than just sine theta cos squared theta on its own. So now I need to figure out how I can convert this into what I want, which is this. And the way I do that is by dividing it by minus 3. So I can divide my guess by minus 3 to get this, okay? So I know I went through that a bit quickly, but I'm kind of going based off the idea that you already understand how to do the reverse chain rule. But if you guys want me to explain it in like a more detailed fashion, then just let me know and I'll make a separate video on it. So the next thing, so we've done the first kind of integration. Now we need to do the second one, which is minus sine theta cos to the power of 4 theta. And the way we do this, again, we kind of look at this. We notice that the differential of cos is minus sine, and we've got a minus sign here. So that kind of screams to us that we need to use the reverse chain rule. So our guess is going to be cos theta to the power of 5. Again, you can use to the power of 5 because you always reduce the power by 1 to get 4, which is what we need here. So I'm using 5. Now again, I've differentiated the guess using the chain rule to end up with this. And you should notice that that is very similar to this. And all we need to do to convert it is divide it by 5. So we divide our guess by 5 as well to get 1 over 5 cos to the power of 5 theta. So we've integrated it now. Now we can just kind of sub in our limits and then we're finally done. So this is what you should end up with, like this. And then once I've subbed in my limits, I kind of write it like this. So I'll be really careful in the way I write it because I've got the 144 at the front. I want to write the whole thing in brackets and then do my normal square brackets, which I use to integrate and sub in values, right? So I get this, and then I can simplify it all down to get this, and then I end up with this. So that was a really, really long question. It takes a lot of time, and I'm not surprised that it's question 14 in this paper. But if you got it, that's really, really good. And if not, don't worry. Just kind of practice. Make sure you learn from your mistakes. It's not that deep. So again, remember to like, follow, comment, share. And if you're interested in tutoring, feel free to message me. And I offer services in biology, chemistry, and maths at GCSE and A level.